Welcome to Zero Knowledge, a podcast where we talk about the latest in zero-knowledge research and the decentralized web. The show is hosted by me, Anna.
And me, Frederick.
So this week, we sit down with Izaak Meckler from O1 Labs. We are going to talk about recursive SNARKs and updates about the Coda protocol. But before we start in, I want to share a couple things. So first off, thank you to everyone who donated to our Gitcoin grant during this CLR matching period that they had going on. It was really cool to hear from all of you and to see a lot of you come out and support and show us and tweet at us. And that. Anyway, it was really nice to actually see that. There was a little competition going, and I think we fared fairly well in the end. So that's good. Secondly, not sure if you've heard about this yet, but there is a new Zero Knowledge Summit in the works. It's happening in Berlin on March 31st. You can stay tuned for the application form that we'll be sharing on Twitter, but it's actually already posted in our Telegram group. So if you're in there, please follow the link and get your application in. As mentioned, this is a highly technical event, and so will mainly cater to the researchers and engineers working in the field. But still, I recommend getting your application in soon for a better chance of securing a spot. So the last thing I want to share is I just want to remind you about our listener feedback form. So a number of you have already given us some great feedback, but if you haven't yet, please do weigh in. This feedback is incredibly helpful to inform what we should focus on, what we're doing right, and what we're doing wrong. I've added the link in the show notes. It's a short anonymous questionnaire. So if you're a longstanding listener or if you're pretty new to the show, we'd really like to hear from you. Of course, you can always stay in touch with us on Telegram, on Twitter. You can check out our very small but growing YouTube channel, where you can also find videos from the last ZK Summit, if you haven't already seen those. And yeah, I guess subscribe where you get your podcasts. I think I'm supposed to say something like that. We share new episodes every week. This is true. Okay, so now here's our interview with Izaak Meckler from O1 Labs. So this week, we're sitting with Izaak Meckler from O1 Labs. He's one of the co-founders of that company and also one of the creators of Coda. So welcome back to the show, Izaak.
Thank you very much. Happy to be here.
Great to have you back. So I think the first question is just what's new? What's been happening? It's been over a year. I checked, it was December 5th. So it's over a year since we talked last time.
What's new? A lot. I guess I can break it into a few categories. One is testnet happenings. It's now been quite a while, maybe something like 6 months that we've been running regular testnets, and starting to have an active community, people building things on top of Coda, people running nodes, and that kind of thing. So that's definitely one big thing. Another is on the technology front. Things have changed a lot. Well, I mean, I can get into the weeds of all the dirty details of snarkology, but suffice it to say that our cryptography has improved a lot. The efficiency of all the things that we're using has improved a lot over the last year. I'm sure we'll get into a little bit of that. The other thing is that we've so far Coda has been a simple cryptocurrency with just payments. And so as we're sort of moving towards mainnet, we're beginning to think about what is our community going to look like? What is our governance going to look like? What are the economics going to look like? And also, what kinds of applications are we going to support beyond payments? So that's been interesting too, and we can probably get into more of that later.
Cool. So this is the second time, I mean, we sort of mentioned this just before. This is the second time you're on. For anyone who hasn't heard that episode, we'll probably put a link to it in the show notes. One thing you will notice in that episode, and possibly in this one, O1 Labs and you, Izaak, are one of the best creators of words with the word snark in it of anyone I know in this space. I just heard a new one, snarkology. Yeah. That's awesome. There was snarkify. There was a bunch of things that I remember in the last episode you added to my vocabulary. So
I think somehow I shy away from it a little bit, but maybe I should just embrace it.
Definitely. Making up words is not a bad thing.
Also, what was your talk at the second ZK Summit or third ZK Summit?
So it was called Notes from the Snarkonomicon, and it was about all the dark magic required to program snarks efficiently.
Yeah, that's a good one.
One other thing that I would add between like the last time I was on the podcast and this year is I've spent a lot of time thinking about what are sort of the most important applications for snarks, not just in cryptocurrency land, but for society at large. And there's, I think, sort of a paucity of discourse around that, unfortunately, but would also be happy to get into that.
Cool. So I think we should do a little bit of a recap on just what Coda is. It's a blockchain. We've gotten that far, but what is it for? What kind of blockchain is it? And jumping ahead a little bit, it involves recursive snarks. So maybe we do a bit of a recap on that as well. But what in essence is Coda?
So Coda is a fully succinct blockchain, and the whole project, there's an emphasis on having a super low friction developer experience and also trying to make it a very accessible platform, both in terms of, from a technological point of view, anyone being able to run a full node, and also from an economics point of view, which I'm not sure how much I can say about now, but there will be some interesting news forthcoming on that. What does it mean to be a succinct blockchain? It means that unlike with something like Ethereum or Bitcoin, where in order to fully verify the state of the world, one has to replay the entire history, you just need to download a very small, constant-sized, in fact, amount of data, about, maybe some kilobytes, and spend a few milliseconds, maybe up to a second, performing some computation to sort of check that data. And it's, in essence, just as good as if you had seen the entire blockchain and checked the whole thing from the beginning and made sure there was no funny business all along the way. Yeah. And so I think that's really important for a number of reasons. There's sort of like I think an important developer experience and user experience component of it. But I think just sort of on a more fundamental level, I think if you really take seriously the idea of a lot of information and a lot of, let's say, economic value and people's lives and so on being bound up with the bits on some blockchain, I think if it's not fully succinct, if it's not something that anyone really can in principle verify, it's not going to look much different from the sort of opaque information, recording systems that we have at the moment. So that's Coda in a nutshell.
Cool.
I sort of don't remember this, but is Coda a proof of stake network?
Yes. It's also,
okay.
So it's a proof of stake blockchain. It uses a protocol that's based on Ouroboros, but custom, tailored to work in the succinct setting. It's actually the protocol that we've developed mostly due to the hard work of Vanashri Rao, who's a cryptographer who works with us. Yeah, it's really interesting because it's sort of not an obvious problem how to get a proof of stake protocol to work in a world where you can only look at sort of a constant slice of history.
I can imagine that is very hard because in typical proof of stake, you can verify that this amount of stake is locked up in these accounts, and you do these authority set changes, and you kind of have to have that history to see how the authority set has changed over time so that you don't have long range attacks and all these other things. So yeah, I can imagine there's a lot of challenges in doing that.
Yeah. So I for anyone who's interested to learn more, if you Google Coda Boros, which I guess is one of my stupid words.
Not stupid. Memorable.
All right. Goofy, memorable words. Yeah, that's my shying away from it. So if you Google Coda Boros, CODABOROS, you can find a lot more information about it. It's pretty, including, I guess, a photo of me wearing a memorabilia jacket from the TV show Silicon Valley. Kind of
Were you on it?
No, my sister used to work for HBO, and she was able to somehow finagle one of these, Pied Piper jackets that I wore while giving a talk about
Very
Coda
cool.
Boros.
Making up words, or speaking about making up words, Babe is also originally based on Ouroboros. So Babe is the block production algorithm used for Polkadot. And we previously had Aura, and what's actually going to be used in Polkadot now is like a combo of Babe and Aura. And because Ouroboros was in there as well, Parody is terrible at names in general, or good depending on how you define it. Like if you like invented terms and acronyms, then we're good. But this combination of Babe, Ouroboros, and Aura became Babesaurus. But we decided to not actually talk about that.
It's a shame.
Yeah, I don't know. People, I think there's some hesitancy to embrace goofy names, but anyway.
That said, we just had Plonk on like 2 weeks ago, so.
Oh, yeah. There you go.
So we were talking a little bit about Coda and how it works, how it's succinct. But, I mean, something that at least for me clarifies like how the system works as a whole is looking at a transaction. And if we're saying we're doing a simple payment transaction, I have some account balance and I'm making a transaction to you. I give you my account balance and I give you the transaction. How are you actually convinced that I've made this payment?
Yeah. So I guess what it's useful to think about is kind of, think about a blockchain as like a state machine, right? And just think about all of the state transitions that are resulting in the current state. So one of them will be your transaction, right? And we want that transaction to sort of leave its mark on the state in such a way that later you can go back and convince someone that really that transaction, is included in the current state. I think about it like that transaction needs to somehow leave its footprints in the snow of time or something. That's kind of a maybe an overly poetic image, but something like that. So actually what happens is when you submit a transaction, the sender of the transaction has, each account has inside of it like a little hash, which is basically a Merkle list of all the transactions which were sent from that account. So when you send a transaction, it basically gets, consed on or prepended to this Merkle list. And then later, if you want to convince someone that, you really sent them a particular transaction, you can dig it out of the Merkle list and send them a Merkle proof. But, crucially, that's something that's on the sender of the transaction to sort of be able to provide that receipt. It's not something that every node in the network is storing these Merkle lists. They just have the hash, and that's, part of the current state.
So the state root is visible to everyone along with the proof that the state root is correct. And then I send you not only my balance in the transaction, but my balance, the transaction, and a Merkle proof that it's actually in this state root.
Yeah, that's exactly right. Yeah.
Cool.
I want to kind of go back to the POS sort of setup, and I want to ask you a little bit about how, given that Coda is built with SNARKs at its core, I don't know if actually... I realize that the way that you're using SNARKs here and using it recursively, it is more for the purpose of scaling. But there has been sort of talk or suggestions of doing private validator sets somehow. Is this at all interesting to you guys? Do you pay attention to it, or is it separate?
No, yeah, totally. So it's pretty straightforward. Once you understand how Ouroboros works, where basically, block winners are selected via VRF, their VRF evaluation being beneath a certain threshold, it's pretty straightforward to see how that could be made private using SNARKs. That said, there are some fundamental conflicts. Oh, and I should say there are a few papers that, write out how this could be done. But yeah, it's nothing too complicated. Probably the papers are more scary than the actual idea. But yeah, that said, there is a fundamental tension between privacy and proof of stake in the sense that, for example, if you want to have delegation, you need to at least let your delegators know how much stake you have. So there is maybe a tension between delegation in proof of stake and privacy, which makes sense, right? I mean, how can the person you're delegating to, for example, give you the right amount? Well, maybe it could be done. I'm not saying it couldn't be done, but anyway, it's not totally clear. Is
this something you're just sort of paying attention to, but it's not at all built into what you're doing right now? Or is it on your roadmap? Or
yeah, so that's not currently on the roadmap. It is something that I think in certain ways it's nice. But in certain ways also, maybe it's a good thing to know who is winning blocks. Because that's kind of the part of the power structure which is governing the network. And maybe there is something good about that being public.
Being transparent. I hear you. So in the previous episode we actually talked a lot about this concept of recursion. We've just mentioned it a few times in passing. I'm thinking it would be useful for us to do a very short definition of what recursive snarks is again, just to give everyone a context of the space in which you're working and like maybe some of the challenges that you're facing in building this way.
Yeah, for sure. So I guess I would put it like this. Recursion is an important technique for snarkifying a computation which is unfolding over time. So one can snarkify a computation. What does it mean to snarkify a computation? Well, I just mean produce a snark of the correctness of that computation. That's what snarks are for, after all, is convincing other people that you ran some computation correctly on some potentially hidden data. But if that computation is sort of unfolding over time, like, say, the verification of a blockchain, then it's appropriate to use the technique of recursion, or the technique of recursion is very useful. And what is the technique of recursion? It's basically making a snark which certifies a computation which includes the verification of another snark. So in the context of Coda, every time someone produces a block, well, at every moment in time, there is a proof which says, a snark which says, there is a blockchain terminating, which if you had executed the whole thing, you would be convinced that the current state is S or whatever. And then when someone wants to produce a new block, what they do is they make a snark which says, okay, first of all, there was a snark, which I ran it through the snark verifier algorithm, and it said, yep, there was a blockchain going up to state S. And if I apply one new block to state S, I get into a new state S prime. And so you take that whole computation, that whole statement that I just said, and you snarkify it, and you get a snark saying, there is a blockchain that ends in S prime. Yeah, so that's kind of what I was getting at with saying that it's a technique for snarkifying computations which are unfolding over time, where at any given moment in time, you want a snark which certifies, the execution of the computation up to that point.
Yeah, I think so. One of the things that I've sort of started to hear in tandem with recursion, or maybe there might be some overlap in definitions, is when you talk about batching of something and then putting a snark on that, does recursive snarks, is it also a form of batching, or is it different? Like, this is interesting, because I actually hear people referring to both of those things, like batching and recursive snarks, sometimes in the same context. And I think it might be good to really define that.
Yeah, so there is a relationship between batching and recursion. Let me try and explain. And it comes back sort of to this concept of a computation which is unfolding over time. Sort of. And it's the following. So what is a batch snark verification algorithm? It's an algorithm which takes as input a bunch of snarks and checks them all simultaneously in an amount of time which is faster than if you had just checked each one individually. So somehow it's a way of taking, 1,000 snarks and checking them faster than 1,000 times, the amount of time that it takes to check one snark. And the way these algorithms tend to be structured is that there is some sort of accumulated state and goes one by one, iterates one by one over each of the snarks, and somehow accumulates them into that accumulated state. And at the end, there's like a final check that takes the accumulated state and does some expensive thing on that accumulated state to finalize the checking and check that it's correct. And so that expensive thing is amortized over, the 1,000 proofs or whatever in a batch. Whereas normally you would have to do that expensive thing once per snark. With batching techniques, you can do that expensive thing once for this accumulated proof or accumulated bit of state. And the sort of the marginal cost of accumulating each individual proof into that accumulator is intended to be small. I mean, that would be a good batching technique if the marginal cost was small. So whenever you have a batching algorithm, you can use it in tandem with recursion to make your recursion more efficient. And basically the idea is, as you're doing the recursion, as you're saying there was an old snark which verified and, that was the old state and this is a new state, blah, blah, blah. You don't verify it completely. You just say, there was an old snark, and if you do that marginal check that accumulates it into the accumulator, this is the new accumulator. as part of your recursive computation, you fold in the marginal batch verification, updating. And at the end, you'll have the snark which says, I saw an entire history of snarks, and this is the accumulator value that you get from doing that whole history of snarks. And then outside, you would verify that final snark, and you would also perform that final verification on that accumulated state, which is then kind of like amortized over the entire history of that chain of recursion.
Does Coda do both of those things then?
Yeah.
Is this something, because I always understood Coda as like purely recursive snarks, but are you also doing this batching?
Yeah.
And like actually, one other thing on that is if you, on any top level snark, how many snarks are underneath it? How many snarks do you snarkify?
Yeah, so I'll try and answer both of those. So we are doing that kind of amortization over the entire history. We've always been doing, I guess, some form of that. And it was recently, Sean, Dara, and Jack's work on Halo, they recently sort of deployed this technique.
It's from Zcash.
Right, from Electric Boogaloo.
Coin company.
Yeah, they recently applied this technique to build Halo, which is a proof system which, has some nice properties. And I should say, like, in our new SNARKitecture, this is another one of my snark words, we're applying even more of these batching plus recursion techniques a la Halo to get a very efficient overall SNARKitecture. In response to your second question about how many snarks does the top level snark or whatever stand in for, or like how many are sort of inside of it. Yeah, it's like I contain multitudes. They have it basically, there's like there's basically like one snark for every transaction, you could say. And then those are arranged in a tree. So like on average, there's kind of 2 snarks per transaction. It's like a binary tree. Then there's also one snark per block. So yeah, a lot. So our current testnet is up to like, I don't know, like some number of thousands of blocks. I don't know. So, that's like, it's kind of crazy. It's like there's this one snark that has inside of it like hours and hours of computation right now on our testnet. Kind of cool. It's probably the fattest snark that ever existed.
Could be your tagline. Fat snarks.
Yeah. One day I hope to see many more fat snarks. Fatter and fatter. Okay.
So when we're talking about recursion, there's an immediate question for me, at least, especially as we like recap it. What is the trade-off of recursing? Because there has to be some trade-off that you have to make, or are all snarks recursive and you can recurse in any of them and it's fine?
No. So you need to like set up the cryptography just right to make recursion possible, or at least efficient. You could always do recursion with any snark. It's just unless you sort of set it up to be efficient, it's going to be insanely inefficient. I want to just kind of call it in particular the work of Fractal and Marlin in clarifying, well, especially Fractal, but I guess Marlin was sort of how they got there, in clarifying what it is that makes recursion possible, or what it is that makes a certain kind of very efficient recursion possible. It's basically this idea of pre-processing. They call it holography, which is sort of just a scary way of saying pre-processing, which is just the concept of taking a circuit or, a computer program and performing some expensive pre-processing to turn it into a small representation, like a sort of a verification key or whatever. So, if you're interested in, I think, understanding maybe on like a structural level, how recursion works, when can you do recursion in a proof system, the work of the Fractal paper is really great for understanding that.
Yeah, we plan on having them on pretty soon, so we'll definitely dig in on that. That's awesome.
You've already mentioned that you have testnets, but I'm curious to hear if you plan on doing any sort of incentivized testnets. I mean, that is certainly the trend, and especially in proof of stake blockchains, since game of stakes was a thing.
Yes. So up to now, our testnets have been using, just sort of points, basically, which are, I guess you could say, just for bragging rights. But we are very soon going to be announcing what we're calling our Genesis program, And that's going to be a token grants program with tie-ins to participating in our testnet. If you're interested in that, please check it out on our website, codaprotocol.com, or on Twitter. It's a great way to, get involved in the test network and make some coins. Check it out.
Are you doing other community things to get people actually participating in this? What is launching a testnet like for you guys?
We've been running our testnet for some months now. We have about 150 participants at this point, and there's been a lot of exciting activity with people, using our GraphQL API to build a block explorer, and we have now a very active Discord chat with people who are running nodes on the testnet, people making issues, people submitting bug fixes. So it's already, even without having this token grant program, been a pretty active community. It's really cool to see because, you're sort of spending months and months and months developing this thing, and to actually have it out there and have people running the software and, it really living, it's it really being real, and this having this out in the world has been really cool and really exciting. And I would say if any of the listeners are interested in participating in this unfolding computation, this giant Snark, I don't want to sound too grandiose, but I think they are sort of a fundamental technology for society in the sense that they allow us to build computer systems that are accountable to their users. If you want to participate in this sort of new capability of our society, a great way is to run a node on our testnet, producing Snarks, compressing the history of the blockchain, making it so there is this tiny chain that anyone can check on any device, including mobile, browser, etc. Yeah, check it out, codaprotocol.com. Wow.
Yeah, do you think most of your, talking a little bit about your community, do you think they're there mostly because they're Snarks enthusiasts? Have you tapped into the ZK community in a big way? Or is it more like engineers that are more, I don't know, coming from blockchain?
It's a mix. There's definitely people who are Snark enthusiasts, and especially I can't even remember when it was now. I think it was over the summer. We had this Snark challenge, which was basically a competition to speed up Snarks. There were $100,000 in prizes for people who made the fastest implementations and modifications to the proof systems and so on. And so that was one way that we built a lot of the part of our community that's sort of enthusiastic about Snarks.
Speaking about those speed ups, I'm curious to hear a little bit about, we touched on this right at the beginning, what is new, what's been happening, and you this is presumably one of those things. What are the innovations? What are the things that came out of this, and how have you sped up the processing in general over this past year?
So there have been two categories of improvements which have unfolded. One is kind of implementation level improvements, and that includes stuff like the GPU prover that we've been working on and stuff like that. And then there's also algorithmic and proof system improvements, and both of those have improved a lot. So on the implementation side, we have been working with someone who, we found through the Snark challenge. Through that, we have a GPU implementation of a Snark prover it's about, I think it's a bit over 4 times faster than a 16 core machine or something like that. So quite performant, especially if you have a computer that already, is just sitting there with the GPU. It's a good way to get a very significant speed up. But there have been a lot of improvements algorithmically. So that includes things like this new Snark construction that I mentioned. That includes things like the new arithmetic circuit-friendly hash functions that have been coming out, and also sort of subsequent improvements on that we and others have made.
New Snark, what does it mostly resemble? So we've had on the show Plonk, we've talked about Sonics. We're going to do episodes, as mentioned, on Fractal and some other of these kind of constructions. Are you creating your own? Are you using existing ones that have come out? What's it look like?
So this new construction that we're currently in the process of implementing, it combines basically the AHP, or a modified version of the AHP, the algebraic holographic proof, whatever, from Marlin, a modified version of it, one that's a bit different from what's described in the paper, just to be sort of maximally efficient in this particular setting, with partially the batching technique from Halo and partially the batching technique that applies to pairing-based Snarks. So it's a
It's a Franken-snark. Come on, you've thought it.
I almost said it, but yeah, it's kind of a Franken-snark, but they all are. So,
So are you coming up with a new name for yours?
Well, I kind of wanted to call it Pickles, just because I love pickles, and it's kind of, I've been floating Pickles as like there is some hullabaloo about the Coda name, and I was floating Pickles as like a joke name, because I really love it. It's sort of, so to me it's very cute and goofy, but so the directory on my computer that has the library of the implementation of the Snark is called Pickles. So maybe
one day it will be named Pickles.
That's amazing.
Maybe it will still be named Pickles.
So what do you mean? Like, you just mentioned sort of new name. What do you mean by new name? What's this all about?
So it's a matter of public record, but there was some kind of legal interaction with R3, who has a project called Coda. Maybe that's all I'll say about that. And if you're interested in learning more about it, you can Google it.
But so you're just sort of like thinking about maybe in the future changing the name.
That's right. And I'm still gunning for Pickles. I don't know if the Pickles will ever make it out of the office or this conversation, but you heard it here first. Pickles coin.
I had asked, just in that previous question, I actually asked where you started from in terms of Snarks. You kind of mentioned where you ended up, but where were you before?
Oh yeah. It's been a whole journey through Snarkonia. So first we were using just Grot16 with the M&T cycles, and then at some point we needed simulation extractability, and we were using half Grot16, half sort of a version of Groth Mahler 2017. And then for efficiency reasons, we switched to using, instead of Groth Mahler, we ended up using this Bo Gabazon modification of Grot16 to make it simulation extractable. And then I think that's probably what's running on our testnet now. But now we're in the process of switching to this new Pickle Snark.
What does it mean to upgrade between these different Snarks? Because let's say you have this testnet and you come up with a new Snark and that's what you want to use there. Do you have to restart the whole chain? Do you have to throw it? Can you actually migrate stuff?
That's a great question. And it's one that there's been a lot of discussion about over the past few months. In our testnets, we have just been killing the network and restarting it when we make that kind of a change. And we preserve balances across iterations, but otherwise, let me say, it is possible. It's generally possible, as long as, say, the fields that you're using remain the same or compatible in some way. It is possible to preserve this Snark and have kind of this new Snark with the old one kind of grafted onto it. And that's most likely the direction that we'll go when Coda is actually live, running mainnet. But for the testnets, we've just been killing, let me not use such violent language, but we've just been deprecating and just replacing the old Snark with the new one.
How do you preserve the balances then? Is it just moving the state root over and putting that in the Genesis block of the new one?
Exactly.
How many testnets have you had?
Oh, that's a good question. We have them on a pretty regular cadence, once every 2 weeks or so. We will run a new testnet with new goals. So every time we run a testnet, we have some particular goals in mind, some particular features we want to exercise, or things that we want people to try out. At this point, I don't know, a dozen or something like that.
Do you also what's your plan in terms of how much testing do you still see having to happen before you can actually launch? I know it's hard sometimes to predict the date, or maybe you have, I don't know, but
yeah, it's really just a matter of when things are ready, rather than having maybe some exact amount of testing in mind or whatever. But
would you say you're half done? Or a quarter done? I don't know. Maybe that would be helpful.
Yeah, so there has been sort of a tension between okay, how many features do we want to make it in before mainnet, and versus how early do we want to launch and so on. I will say with confidence we will definitely be launching sometime later this year in the not too distant future. Exact date forthcoming. And if you want to know, one great way to know is by participating in our testnet and seeing how beautiful and polished the software is. Or not,
Cool.
as you might find.
Something that was interesting to me in what you talked about, like what's been going on, is the implementation side. So I think if I remember correctly, you've written everything in OCaml, and I wonder if that's still the case. But particularly this GPU thing, I wasn't under the impression that SNARKs were particularly parallelizable. Like it was pretty hard to parallelize, and that's why Izaak exists and it like explicitly attempts to parallelize to some degree. Maybe that's making it distributed and more than parallelized. I don't know. So I'm curious, just like what does this GPU construction actually look like? Why is there such a speed up in this world?
Right. So the Coda daemon itself is written in OCaml, but some of the crypto code is written in C++ and Rust, and in the case of the GPU prover in Coda, or Coda C, or whatever you want to call it. In fact, like Snark provers are extremely parallelizable. Producing a Snark has maybe, let me say, 3 steps. One is going from the kind of raw witness to the witness vector, which represents like the satisfying assignment of the constraint system. That's usually a pretty serial computation. So, but also it's pretty fast and a minor part of the overall proving time. You know, that you just do on CPU and that's fine, whatever. You produce this witness vector. But once you have that, and once you want to take this witness vector and compress it down into a Snark, typically that computation involves 2 things, 2 kinds of core computations. One is FFTs, fast Fourier transforms over a finite field. And essentially what this is like interpolation of polynomials. So, you know, if you have a bunch of points, say if you have d points, you can make a degree d-1 polynomial that goes through all of those points. And that's an important part of pretty much every Snark construction, is performing this kind of polynomial interpolation. That algorithm is itself, quite well parallelizable, but then there's this other component, which is multi-exponentiation, or in additive notation for the real cryptography heads out there, multiscalar multiplication. What do people say? So awkward. Multiscalar multiplication. And that is an extremely parallelizable algorithm. That is to say, there are algorithms for performing multiscalar multiplication which are embarrassingly parallel.
Interesting.
And it's the sort of thing which is very well suited to execution on a GPU.
That last step.
Yeah, the FFTs are too, but they represent a smaller proportion of the overall computation time. So the biggest win is by putting the multi-exponentiations on the GPU.
You just sort of started this paragraph with there's 3 parts. I just want to check if I got them. It was the first part witness to vector, second part FFT, third part multiscalar multiplication.
Yeah. And you know, depending on the Snark construction, like sometimes you like do some FFTs, and then like you do some multiscalar multiplications, and then like you do some FFTs, and then you do some other. So it kind of goes back and forth. But those are sort of the three components. The first part, witness generation, is usually so small that it's not really even, people don't even really talk about it very much because it's usually just a very small component of the overall proving time.
Cool. That's actually super helpful. Don't know if I've ever heard it said that way.
Yeah, I've never had a breakdown of the computational steps like that. It's explains it perfectly well.
Glad to hear it.
A lot of sort of blockchains that are very focused on like token transfer. What I've seen, at least in proposals, is a lot of them are kind of contemplating trying to incorporate some sort of computation. Are you guys exploring that at all? Are you thinking of like adding more to this whole construction so that it's more than just transferring?
Yeah.
Or that more than just transferring is possible?
Yeah. So I think one false narrative that has persisted for a while is that it's sort of, you can't do general computation using inside of SNARKs or something like that. And that's totally not true at all, especially when you're pairing them with recursion. So we have been discussing how to support general computation on Coda to support applications like escrow and voting and, you know, DeFi stuff and other kinds of applications that we can get into later. And in particular, we currently have an RFC up that's, you know, where devs are working through, which is on our GitHub. It's like pull request 4191, which has a proposal for how to do general computation on Coda. It follows the same kind of idea of something like ZEXE, which uses recursion and SNARKs to have a system for doing general computation in an optionally privacy protecting kind of way.
And so that would mean it's not a full smart contract platform when we're saying that. It's like you can do some kinds of computation.
So, depending on how that RFC shakes out, what kind of computation will be supported at launch is a little bit up in the air, but it will be possible to do pretty much anything, I think. For some reason, I don't want to call it smart contracts because I feel like that implies like this particular programming style where like you have these, it's kind of like an actor kind of model. And I don't know that it will look exactly like that, but you will be able to sort of set up applications that, have their own internal state transition logic that, is totally customizable by a programmer.
I think anyone who understands ZXE or ZXE, depending on how sexist you want to be in calling it.
I remember the first time, I think it was somebody said it and I was like, what? But now I don't even notice. Anyway.
But I think anyone familiar with that system will understand what you mean. Like, it does look very different. It doesn't look like Ethereum smart contracts. But I think we should, as an industry, broaden the term of smart contract to mean things like this as well, because I think they are, like, by the original kind of definition of smart contract.
Okay, sounds good. It's smart contracts. Check it out. Pull request 4191.
Cool. So I think one thing that I'd be curious to hear from you about is what inspires you really to work on this stuff, on SNARKs, on $0 stuff? Is it like, I think we might have covered this in the last episode about your background, but were you getting into this because of the blockchain? Were you getting into it because of the SNARKs? And what do you think could actually come out of that?
Initially, I was somehow just kind of captivated by the idea of, having a computation that could run for 1,000 years and then being able to produce this tiny little proof and convince someone of the correctness of that computation. And I think at first that was very inspiring to me. Since then, I would say this is sort of like in tandem with like my general political radicalization. I've become more interested in, could say, liberatory potential of this kind of cryptography.
And you're talking about SNARKs here. You're not talking about like general blockchain technology.
Not blockchains. Yeah. I mean,
SNARKs.
Yeah, blockchain, sure. But like in particular, SNARKs. I think somehow like SNARKs are at their most useful when you pair them with like a verifiable public state machine. But I think SNARKs in general have a lot of liberatory potential, if I may say that. Or one kind of framing I think that makes it very clear is right now, we interact with computer systems that we just have no oversight over at all. We have really no idea what they're doing. They're complete black boxes. They can abuse us in whatever way. I mean, to give a very tangible, concrete example, there are a lot of lenders, creditors or lenders who make, racist or sexist loan determinations. That's a problem in society. And, it's an injustice that we should seek to redress. One thing that we could say is, for example, well, all right, they shouldn't be allowed to do that, and we should have some kind of oversight. Maybe there should be some public process through which we vet the algorithms that they're using to make these loan determinations or whatever. Because right now it's just some black box, in Goldman Sachs' basement or whatever that's spinning out. You get this much at this rate, and that's wrong. And there's real damage and violence done as a result of that. And one way out is, as I said, we could have this public vetting process whereby, we somehow come to a consensus about what sort of algorithm is sort of acceptably biased, whatever that means. And, that's like a complicated political question about how can we actually have a process to come to that kind of decision. But once we've come to a kind of decision that, all right, this is the sort of algorithm that we're comfortable with using as a society, then you get into the question of actually enforcing that lenders are going to use that algorithm. Because in our current system, there's no reason for them, even if they publicly commit to using a particular algorithm, there's no reason for them to actually use it. I think, for example, about the Volkswagen scandal, where they were, during inspections, they were using this fuel efficient mode or whatever, this like no smog mode. But then, they had their car have software which detected like, oh, we're probably in the inspector's office right now, so we should like pretend to like be clean or whatever. And then on the road, it operated in this sort of smog producing way. So to draw the parallel with SNARKs, let's say we all get together and we agree, okay, this is the good algorithm. This is an acceptable algorithm for making loan determinations. Here's what we're going to stick with. That is not necessarily super meaningful in terms of actually enforcing that the lender uses that algorithm, unless each time it actually makes a loan determination, it provides some evidence that it's using that algorithm. And that's a perfect application for SNARKs, because that's precisely what SNARKs let you do. We can imagine a world where lenders are mandated by law or community consensus or public opinion to, every time that they make a loan determination to someone, provide additionally a proof which says this loan determination was made on this input data, your personal information, whatever, using this agreed upon algorithm. SNARKs could actually, be used in that way to enforce the use of a given approved algorithm. It's not going to help solve the problem of what is a good algorithm, what is like a non-racist or non-sexist algorithm or whatever, but it at least gives you the tools to enforce that decision at scale across a society.
Although, and I don't want to be the pessimist,
yeah,
but the other side of that is, what if there was a really corrupt algorithm or like some corrupt decision? Then it would also be enforceable, I guess, through this.
But it would be transparent what algorithm you're using. So if a racist loan provider publishes their algorithm and says this is racist, then I'm just not going to use that provider.
Right. I mean, it's no worse than the situation that we're in now, where it's just a black box.
Yeah.
What's going on?
So in this case, I think it's sort of the type of use case that you're describing there, I would say, falls a little bit into this like verification category for sort of use cases of zero knowledge proof technologies, where it's like verification or certification of some sort. And I've heard a few examples of that. I gave a few examples in this article that I published over the holidays. But actually, this is a space that's super fascinating. The ways that you can replace that third-party kind of checking body, or provide a third-party certifier in the case where there doesn't exist one, but that certifier be math. I like that example.
Yeah, right. It's like we build this little homunculus who is homunculus regulator who's watching every computation and making sure it's following the rules.
And at the same time, could actually also keep certain things private. In the case that there are some, like, I don't know, some other properties of these algorithms that are proprietary or, something that wouldn't want to be shared publicly, you could potentially include that as well.
Yeah, totally. I mean, I think especially it could be interesting in this just to stick with this example. Maybe the lender, for whatever reason, they want their lending algorithm to be private. Well, that's fine. They can still prove, this algorithm that I committed to, if you run it with this input, this is the result that you get.
Hmm. So before we sign off, is there anything else that you'd like to share?
There is one thing that I wanted to communicate that I feel like I didn't quite communicate.
What is that?
If it's not clear, well, I want to kind of make the case for like why it's actually extremely important. Well, it sort of dovetails with what you were saying about this like checker or whatever, about why it's important for blockchains or cryptocurrencies in particular to have this kind of totally succinct verification with using SNARKs.
I think it's something we touched upon tons of times, and especially talking about like stateless clients. So it's a recurring theme, and I think it's worth reinforcing. So basically, being able to say, like, if you look at Ethereum or Bitcoin today, people don't run nodes. They just rely on some centralized infrastructure to tell them what the state is. And the reason they don't run nodes is because it's too heavy. So, yeah, if we actually want technology to be decentralized, it needs to be way, way lighter than what a Bitcoin full node currently is.
I mean, and like if you really kind of think out what happens in a world where, right now, if someone it did a bad state transition on Bitcoin or Ethereum, not very many people's lives would be dramatically affected by it. There's not the fates of not too many lives are bound up with the bits of those blockchains. But if you were in a world where there were millions of lives of people's lives and at stake with with regards to what happens on a particular cryptocurrency system. Personally, I think it's pretty clear that someone would just make an invalid state transition if there were no sort of actual widespread oversight over what's happening. There's just not really enough kind of at stake to sort of do the collusion required. But I believe very strongly that it would happen if these things were sort of existing at the scale of an entire world or an entire society.
And so what do you recommend?
Well, I mean, that's why, we do need to have this fully succinct architecture, because it makes it possible for any device, like a browser, a phone, whatever, literally everyone, to have the kind of complete oversight, to have this little regulator who's, enforcing the rules of the system, the socially agreed upon rules of the system at every point. I think it's important not to be naive. Technological utopianism is very popular in the crypto space and in technology industry in general. That's not at all my position. I don't believe that technology inherently solves any kind of problems or whatever, but it is a tool with which we can, come to a political consensus, a social consensus as to what sort of behavior or what sort of operations are acceptable in our money system, in computations in general, and then we can use these tools to enforce them at the kind of scale that it's not possible to today.
Well, listen, I want to say thank you so much for coming on the show and sharing with us this update, sharing with us some of your thoughts on the latest zero knowledge stuff, the work that you guys have been doing, and also these ideas of like real world applications. And I think you went past that actually in what you just said. It's not just application, it's like the reason this matters. So thanks for sharing that.
Oh yeah, my pleasure. I think it's something that's really important and that people don't think about enough, I think for explainable reasons, but nonetheless, I think it's an important thing to spend time talking about.
Cool.
And thanks again for having me on the show. It was a lot of fun.
Thank you very much. And to our listeners, thanks for listening.
Thanks for listening.